Hey kids, welcome aboard. Welcome to today's episode of Uncle Vern's Chemical Circus. Today we learn about making mass in grams to mole calculations. And what you see in front of you, and by the way, what you should have in your possession at this very time, is an illustration of what I refer to as the mole roadmap. This is going to be extremely handy, so make sure you maintain possession of it. Today, we're going to look simply at this lower left-hand corner of it. We're going to look at beginning with a mass in grams and converting it to moles. And typically, what that will involve is using a unity fraction involving 1 mole of whatever the substance is over its molar mass. So let's take a look at some sample calculations. As always, when we begin to work sample problems, the things we need to have out available are going to be a piece of paper or something else to write on, pen or a pencil, calculator, periodic table. Probably want to have your handout of common oxidation numbers available, and later on in a couple of these problems we'll probably want to have our rules for naming and writing the formulas of particular acids. So go on and make sure you've got those things available. If you've got them all, then we're ready to proceed. I want you to notice how I've highlighted the phrase mass to moles. Okay? We can make the reverse calculation, which we're going to do here in a few moments, but right now I want to make sure that you're quite clear. These are mass in grams to mole conversions. And our first one simply deals with an element. The element is copper, element number 29 on our periodic table. And the first question I need to ask is, what is the average atomic mass of copper? You may recall that copper is one of those elements whose average atomic mass we do not round off to the nearest whole number. Copper's average atomic mass for our purposes is 63.5 AMUs. Well, that's for a single copper atom. I'm not interested in the mass of a single copper atom. It's far too small for me to work with. So what I really want to know is, what's the mass of Avogadro's number of copper atoms? In other words, if I had 6.02 times 10 to the 23rd copper atoms, what would be the mass? In other words, what I'm really asking is, what's the mass of a mole of copper? And by this time, most of you are quite comfortable in saying that a mole of copper has a mass of 63.5 grams. With that in mind, we can start the solution to our problem. We start with our 250 grams of copper. And I want you to notice that I'm going to be very specific in my units here. It's not simply 250 grams, it's 250 grams of copper. As we progress through these problems and on into Chapter 9, these designations become more and more important for tracking our problem solving. So make sure that it's not simply grams, but grams of copper. Okay? I want moles, so I'm going to put moles in my numerator here. What's the mass of a mole of copper? We've already established that's 63.5 grams. And when I do my work on the calculator, I'm going to get 3.937 moles of copper. I'm looking at 4 significant figures there. Go back to my original information here. You'll see that what I've got is a value 250 grams. Ask yourself, how many significant figures am I looking at there? And the answer is quite clear. It's 2 significant figures. Don't worry about what we've got down here from the periodic table. Go back to the information that I gave you. And since I've got 250 grams and that reflects 2 significant figures, let's use that for the specific number of significant figures in our answer. In that case, it would be 3.9 moles of copper. Let's take a look at our second sample problem. How many moles are there in 76.0 grams of nitric acid? Once again, we're being asked to convert a mass in grams, in this case 76.0 grams, to moles. What makes this problem slightly different, however, is unlike the previous sample problem where you were working with a chemical element, in the case of sample problem number 1, which was copper, in this problem you're going to be working with a chemical compound, nitric acid. What makes this slightly more challenging is the fact that I'm going to require you to write the formula for nitric acid. That's why I recommended earlier that you have both the handout of common oxidation numbers as well as the handout associated with naming acids and writing their formulas. So, with that in mind, a couple of diagnostic questions here. Nitric acid, binary or ternary acid? Well, if it were a binary acid, we would see the prefix hydro here. We do not see that, so we have just eliminated the possibility that it is a binary acid. So it's a ternary acid. So if you have that handout available, you'd turn over to the back side where you see the information for writing the names and formulas for ternary acids, and you would look to see which pattern does this fit. Well, a ternary acid ending in the suffix IC generally is derived from hydrogen blank ATE. So in other words, hydrogen nitrate is the formula or substance from which we derive nitric acid. So with that in mind, we go to our handout of common oxidation numbers, and we can determine rather quickly that the formula for nitric acid is HNO3. Once we've done that, we're going to need to convert to moles. And in order to do that for a compound, we have to calculate a formula mass. Okay, hydrogen, straight off the periodic table, 1 AMU. How many of them appear in the compound? 1. Okay. Next, nitrogen. Nitrogen has a mass of 14. It is element number 7 on the periodic table, but its mass is 14 AMUs. And it also appears one time in this particular formula. Lastly, oxygen. Hopefully by now you're starting to remember that oxygen has a mass of 16 AMUs. The subscript indicates it appears 3 times in this compound, so that's a total of 48 AMUs from oxygen, and our total mass is 63 AMUs. 63 AMUs is the mass of one molecule of nitric acid. We're not interested in a single molecule. We want the mass of a mole. So if I had Avogadro's number, if I had 6.02 times 10 to the 23rd nitric acid molecules, they would have a mass of 63 grams. So with that in mind, here we go. 76.0 grams of nitric acid. And we're going to be very clear what we're working with. It's not just grams, it's grams of nitric acid times 1 mole of nitric acid. 1 mole of nitric acid, all that over 63 grams. And the result is 1.21 moles of nitric acid. And that's how we go about determining the number of moles in a particular quantity or mass of a chemical compound. First, we have to determine the formula, determine formula mass, and then make our conversion. And lastly, you'll notice up here 76.0 grams. That's 3 significant figures. I'm down here 1.21 moles. That's 3 significant figures. So when it comes to significant figures, I'm in good shape there. Our third and final sample problem, where we convert mass to moles, reads as follows. How many moles of oxygen are there in 76.0 grams of nitric acid? Sounds an awful lot like the previous sample problem that we worked. However, it's this right here, oxygen. What I'm asking for this time is specifically the element oxygen inside that chemical compound. Okay? So first thing we need to do, since again we're dealing with a chemical compound, of course, is write the formula. And the formula of nitric acid hasn't changed. It's still HNO3. And because the next thing I need to do is to calculate the formula mass, I'm going to do that in rather fast motion. Once we have our formula mass calculated, let's do what we always do, convert to moles. Okay? And so what we've got here are 76.0 grams of nitric acid. We're going to convert to moles. 1 mole of nitric acid is 63 grams. So put 63 grams down here. But there's one more thing we're being asked for. We're not being asked for moles of nitric acid. We're actually being asked for the number of moles of oxygen. This formula, when you look at it, constitutes a single mole. That's 1 mole of nitric acid. But the subscripts within that formula tell us certain things. For example, in order to make a mole of nitric acid, because there is an understood 1 right there, we know that it takes 1 mole of hydrogen. We also know that it takes 1 mole of nitrogen to make up a single mole of nitric acid. Well, what does this tell us? This tells us that it in fact takes 3 moles of oxygen to make up a single mole of nitric acid. And what I'm explaining here is something that's going to be extremely useful to us as we continue with stoichiometry. And that's a concept called the mole ratio. In this case, the mole ratio is as follows. For every mole, and we abbreviate mole, M-O-L, of nitric acid, there are 3 moles of oxygen. Well, that's an inequality. And remember, from any equality, we can derive 2 unity fractions. And then we can plug unity fractions into our dimensional analysis and solve problems. So what I want to do here is I need to get rid of moles of nitric acid. So if I put moles of nitric acid in my denominator here, and that would be 1 mole of nitric acid, what's going into my numerator? It's what I'm looking for, which in this case is moles of oxygen. And in fact, there are 3 moles of oxygen for every mole of nitric acid. And this step right here is called the mole ratio. When we do the math, we find out that the answer is 3.62 moles of oxygen. And if you look at your answer to the previous sample problem, you'll notice that the answer there was 1.21 moles of nitric acid. And if you do some quick math, 1.21 times 3 is approximately 3.62. So be aware, the mole ratio step is something that's going to be with us for a long time to come. And now let's move on to our practice problems. Okay, here are 3 mass to mole practice problems. In the very first one, you'll notice that I'm simply asking for the number of moles of nitrogen. I want to caution you, nitrogen, although an element, something about Brinkelhof, B-R-I-N-C-L-E-H-O-F comes to mind there. Hope you got that hint. The second one, convert 1,085 grams of calcium phosphate to moles. Yes, I know you're rather ticked that I didn't give you the formula for calcium phosphate. Tough darts. And then on the third one, please note carefully, determine the number of moles of oxygen in 750 grams of glucose. So this is not simply asking you to convert 750 grams of glucose to moles of glucose, but I'm asking you specifically for oxygen, and that's going to necessitate that you employ the mole ratio step that we were exposed to in sample problem number 4. Good luck.